For the first couple of problems, we're trying to look at a graph and seeing if it can represent a variable with a normal distribution. A quick reminder, for any distribution, the way you're reading it is the values along the x-axis are the different possible values that the variable could take on. And then the height of the graph is representing how likely, how probable each of those values are. So for this picture, it's a normal distribution. The mean, which is right in the middle, has the highest probability of occurring, and the further away you get from the mean, the less likely the values are. And so to look at any graph and identify if it's normal or not, it's going to need to meet all these criteria. The key points, you're going to look for a single peak. It's going to be symmetric around that single peak. And that's how we guarantee the mean, median, and mode are all equal, and that it's bell-shaped and symmetric. So look for that. It needs to be approaching the x-axis on both sides as we get further and further away from the mean, and it should never go below the x-axis. Here are some samples. This one goes below the x-axis, so it's not a normal distribution. This one's not because it has two peaks. This one never approaches the x-axis. As we get out in the tails, it needs to be down close to the x-axis. This one isn't symmetric. It's skewed to the left. This one's skewed to the right. This is our only example here of a normal distribution that meets all the criteria: single peak, symmetric, approaching the x-axis but never going below. And when you have a normal distribution, just looking at it, you can try to estimate the mean and standard deviation. The mean is the value right in the middle under the peak, so it's about 11.5 here. That's what it looks like. And the standard deviation is going to be that point where the inflection shifts. So imagine if you're sledding down this hill and it's very steep. It's getting steeper and steeper. You can tell it's dropping off downhill, downhill. And about right here, it's still going downhill, but it starts to level off and get less and less steep from that point forward. That's called the inflection point, and it's about 13. So that's a standard deviation that would be 1.5, because 11.5 to 13 is 1.5 away. And you can see, again, 1.5 away the other way to 10. We're going to see that same situation where if you were sledding down this hill, it's getting steeper and steeper and steeper, but right around 10 is when it starts to level off and get less steep. So our standard deviation is 1.5 for this example. For problems 3 through problem 8, we're looking at z-values. And I'm going to show you how to do problems like this in Excel. So remember, a z-value is just a measurement of how far away we are from the mean, and it's in terms of standard deviations. So negative 0.99, negative means we're below the mean. The mean's right in the middle of the distribution. And this is almost -1, so we're almost 1 standard deviation to the left of the mean. However big a standard deviation is, it varies from problem to problem. So what we're trying to find here is the area under the standard normal curve to the left of that z-value. And I'm going to show you how to do that in Excel to get this result. Another way of thinking of the area to the left, it's the probability if we randomly selected a value that value is anywhere in this area from that mark leftward. So it's a measurement of the area, and it's also a measurement of the probability of getting a value that falls within that portion of the distribution. So all you need to do is type this formula into Excel. So norm.s.distribution, or .dist, and then our z-value, -0.99, and then we always, then comma, and then we always type true. And that gives you the probability of being from a z-value of 0.99 or anywhere even further away from the mean leftward. And so for this next problem, we're going to look at finding the probability of being at a z-value or even further to the right. Another way of phrasing that is finding the area under the normal curve from that z-value onward to the right. And so we're going to use that similar formula in Excel. We're using our z-value here of 1.06. And if we use just that exact same formula, we get the probability of being, again, to the left of that mark. And so the whole area under the normal curve has to add up to 1 or 100%. So if we just do 1 minus this part over here, then we'll be left with the part to the right, which is what we're looking for. So 1 minus the part on the left gives us the part on the right. So here I've entered our z value of 1.06, comma true. And if I just do 1 minus that, so 1 minus my answer there, that's the probability of being from, um, from that mark of 1.06 rightward. Another thing we can do is try to find the area between two z values, or to try to find the probability that a value will fall between two z values. We're going to use that same formula in Excel, and if we use that formula for 1.25, it would give us the probability of all this blue and also this white part here that's not colored in, everything to the left. And if we use the formula for negative 1.5 here, it gives us just the part to the left here. So if we take our result from 1.25, which would be everything, including this part in white, and we subtract the probability of being to the left of this, we're subtracting off this white part here. And so what we'll have left is just the part that's in between. So let's look at that in Excel. For in between two z values, we use that same formula. We're going to use it for the bigger z value, 1.25. And also the smaller z value, the one further to the left, and we're going to subtract away that smaller one from the big one for our final answer. So to get in between, we need to take everything to the left of the first one and subtract off the piece that's to the left of the second one, and all we're left with then is what is in between the two. For number 9, there's several parts of the problem, and the first one is to draw a frequency histogram. So I'm going to look at this data here in Excel. You can use the max formula to find the biggest value, the min formula to find the smallest value, and then the range is just the subtraction of those two. The class width, then, the problem said to have 5 classes, so I divide the range by 5. And then I need to just add or round up to the next whole number. So starting then with my smallest value, and that's going to be the lower limit of my first class, and then I just add our class width to that value to get the next lower class limit. And you can actually take that and drag it down, and Excel then will keep adding that class width to each successive lower class limit. So 28286 would be our upper class limit here, right below the lower class limit for our second class. So again, if I take that value and I add our class width, I'm going to get all the successive upper class limits then for this data. From that point, you just need to count the frequency, go through all your data and see which class each piece of data falls in, count the frequency, and then from there, you're going to draw your histogram accordingly. And the height of each bar represents how many pieces of data are in each class. Then you'll want to analyze your histogram, see if it's bell-shaped, see if it's symmetric or skewed, just answer that question then about its shape. To find the mean and the standard deviation, you can do that in Excel. Use the average function here to get the mean, and standard deviation.s because we have a sample, and that'll give you the standard deviation for your sample. And then wrap up just by comparing those values to what the problem stated the manufacturer was claiming for the mean and standard deviation, and interpret that result. For number 10, we're looking at a test here, an exam. We have the mean score for the exam, we have the standard deviation for the exam, and then we're looking at some random student scores, and we're going to find the z-score for each of those values. Remember, our z-scores are measuring how far away we are from the mean in terms of standard deviation. So we use this formula. We take the value, subtract the mean, and then divide by the standard deviation. So with these values, if we're looking for the z-score of 1940, we would take 1940, subtract the mean, and then divide by the value of our standard deviation. And so that tells us that this score is 1.328 standard deviations above the mean. And the next part of the problem is asking if any of the values are unusual or not. And how we determine if a value is unusual or not is if it's more than 2 standard deviations away from the mean, we call it unusual. So if your z-score comes back here to either a +2 or bigger or a -2 or bigger, we say that's an unusual value because it's pretty far away from the mean. So it doesn't occur very often, it's unusual. And just looking at the probability of being that far away from the mean, if you type this into Excel, you see the probability of being 2 standard deviations or more below the mean comes out to about 2.3%, so very unlikely. That's why we're calling it unusual, because the probability of it happening is not very high. And the remainder of this assignment, 11 through 16, are almost identical in computation to what we did for 3 through 8. So it's just phrasing the question differently. Here it's saying find the probability of z occurring in the indicated region, as opposed to what we looked at in 3, which was find the area of the shaded region. But the area and the probability of it occurring are actually two different ways to think about the same exact concept. So again, going back to what we did for 3 through 8, you're going to use these formulas in Excel. This one for left of the probability for being left of a certain value, 1 minus for the probability of right of a certain value, and then use the formula for both values if you're doing in between, and just subtract the smaller one from the bigger one.